Just as we can derive the entire language of mathematics from formal propositional logic, we can equivalently derive it from the language of sets. So this is another way to begin. In the same way as we say, oh, look at trig functions, they come from these triangles, but they also come from the unit circle. The rules of math come from the rules of logic. They also come from the rules of sets. But a set is a pile of stuff. Really, that's all it is. It's an unordered collection of things. The term objects here is deliberately left vague. The term collection here is deliberately left vague. Unfortunately, this does lead to some problems, which we'll discuss in a minute. It is possible to label or describe a set quite frequently. We use these sort of curly braces to define a set. I can think of the set of all the books in my office, the set of all the students in a class. I can think of the set of even integers. And think of the set of my daughters. But what I've done is I've given a definition. An object must have this property, this description, to be a member of this set. So the items in a set are members or elements. The problem is this descriptor. I've just defined a set by describing. I have one child. That child is not a daughter. This set has no elements. It's empty. On the other hand, clearly, there are students in this class. If I really want to be pedantic, I should be very specific. This discrete mathematics class, this semester, and so on. And then I know immediately whether someone is in or not in that set. Same thing with books in my office. Same thing with even integers. I have a definition of a property that goes here. The objects in the set are members. A set contains its elements. So the set, books in my office, contains this one. And I mean that literally. I have a copy here. There is another copy sitting in my office right now. So books in my office includes this book. Today, it happens to include a copy of Catholic Higher Education by Father John Heft. It's for a meeting this afternoon. But it's sitting on my desk. My copy of Harry Potter is at home. It's not in my office. That's not an element of the set. But by leaving this descriptor, we come to a problem. A set is well defined if I can tell whether a thing is in the set or it isn't. So I can look at a book. I say, yes, I have a copy of that book in my office, or no, I do not have a copy of that book in my office. It would be better if I had a list of books in my office I could check it against, but I know the books in my office pretty well. I have a list of the students that are in the class. I can look at a person and say, yes, you are a student in the spring semester of 2026 discrete math class. I can look at a student and say, no, you are not a student in this class immediately. Here's a set of almost even numbers. Do you know what almost even means? Neither do I. So is a number in this set or not? I have no idea. So this is badly defined. It's not well defined. Doesn't make sense. But even if I could give you an explicit definition, I might still not be able to have a set. I want you to think about a book. I don't care what book it is. In the book, somewhere, is there a reference to another part of the book? For example, our textbook. If I'm in chapter 1, section 5, where I talked about nested quantifiers, it's going to say, hey, back in the previous section, we talked about this quantifier, and okay, that refers to another part in this book. That book does refer to itself. In The Three Musketeers, The Three Musketeers was actually released not as a book originally, but it was released each chapter separately as a serial. Came out in the newspaper once every 2 weeks. You got a chapter every 2 weeks. Kind of like modern fan fiction. Oh, here's another chapter. Here's another chapter. If they refer to the previous chapter, as we saw in last week's episode, do they do this on TV shows all the time? Hey, last time on, that refers to itself, doesn't it? So the book, Three Musketeers, does refer to itself. On the other hand, as I said earlier, Harry Potter, if I'm reading Harry Potter and the Sorcerer's Stone, it doesn't say, back in chapter 5 we saw, because the book isn't written that way, right? There are a lot of books that clearly do not refer to themselves. I'm going to go through the library here at Seton Hill. I'm going to write down all the books that do not refer to themselves. I'm going to go to the Library of Congress. I'm going to write down all the books that do not refer to themselves. I now have a big-ass list, don't I? I print it out, and I bind it. It's a book. Does that book refer to itself? If the answer is no, then it should be on my list. But as soon as I put it on the list, it refers to itself. It can't be on the list. Oh, fuck. If it's on the list, then it can't be on the list. If it's not on the list, then it should be on the list. What the hell am I supposed to do? So even when I have a good definition, I may still be unable to resolve this sort of paradox. This, by the way, is a variation from Bertrand Russell of Russell's paradox. A paradox is a sentence that is supposed to be true and false at the same time. It's not a valid proposition. I can't use those. So what Bertrand Russell did to avoid this idea is he said, we can only use well-defined sets in the same way that we can only use well-defined propositions, right? It's either got to be true or false and not both. Russell said you have to be able to tell whether something is in or not. And if it isn't, you can't use that idea. If I have a descriptor like this. This is referred to as set builder notation. You've seen this a lot, where we write down a set by describing the things that go into it. Typically, we'll have the name of an arbitrary kind of element, X. And then we'll have this little vertical bar, and then we'll have some property. Hey, wait a minute. What I'm really defining here is a proposition, aren't I? P of X, a propositional function. This is a property about X. If that property is true, X is in the set. If that property is false, X is not in the set. The exact same idea as a quantified statement. So if this set has elements, those are the things there exists in X for which P of X is true. If I have, rather than a list, rather than a description, I have a list. Well, let me not do it that way. This sort of list of a set is a roster. So I can either describe it by a property, or I can describe it by explicitly listing it. And I'll only use these ellipses, these dots, when the pattern is obvious. That sentence right there is going to piss me off more often than I can think. Because what is an obvious pattern ain't. We'll talk about that more in another section. But the way in which that pattern needs to be clear means I need to be able to tell immediately what's in the set and what's not. I want all the multiples of 2. The objects in a set don't have to be restricted to any particular type. So for example, this is a perfectly good set. I have no idea what this set is, but Pittsburgh, Pennsylvania, Red, 2, and Jacob, that's a set. So I have several different ways of indicating a set. Ideally, I like this set builder notation. I'm going to read that vertical bar as either so that, kind of like we read the comma in our for all X, P of X. For all, take the X's so that this thing is true. Take the X's so that this property holds. Questions? I'm a math guy. The sets I use the most often are sets of numbers. Page 125. The most commonly used sets in mathematics as sets of numbers. And I'm going to start with an argument. That very first set is the set of natural numbers. I want you to start counting. If I tell you to start counting, what do you start with? This book starts with 0. Some definitions of the natural numbers don't include 0. Some do. Our textbook does. I hate it. Because to me, the natural number starts where you naturally start counting. I start with 1. Although I suppose that's from growing up American. Because the first floor is the floor you walk in on. If you grew up in Britain, the first floor you walk in on is the 0th floor, the ground floor. 1 is 1 up. But these are whole numbers. Z, for the German word Zahlen, integer, includes all the positive and negative whole numbers and 0. If I put a little plus on it, then I'm only referring to the positive parts. Q for quotient ratios are integer over integer fractions. 13 over 7, 2 over 23. Ideally, I'm going to reduce my fraction to its lowest term. I could write 4 over 8, but I might as well just write 1/2. Notice that we're saying the top is an integer, the bottom is an integer, and the bottom can't be 0. So there's my description in set builder notation as opposed to in roster notation. R is the set of all real numbers. So now I include things like the square root of 2, which I know isn't rational. So it's definitely in R, but not in Q. Or the square root of 7, or the cube root of 14, or pi, or E, or all sorts of other crazy numbers. If I only want the positive ones, that's fine. By the way, you could replace that plus with a little minus, then you only get the negative ones. There are places where we want to exclude 0. If I want to exclude 0, I'm going to put a little star up there. Then there's a set of complex numbers. Complex numbers, that's like the square root of -2 with the I on it. So a complex number is a plus bi, where a and b are reals. And please note it says so right here. Some people do not consider 0 to be a natural number. Make sure you check which book you're using. Our book does twitch, twitch, twitch. A lot of these usually show up in a drawing showing the containment of one set in another. We'll talk about that in another minute. Questions? A set is unordered. Two sets are equal if they contain the same elements. But because a set is unordered, all of those are the same. A set also doesn't distinguish between things in it. So here's another set. Are you ready to be pissed off? This set is equal to the other 3 as well. Grace, I saw that face. I made that face. The very same thing I made. I think, no, no, wait a minute. But let's check. Remember, 2 sets are equal if they contain the same element. I have a 1. Does this set contain a 1? Yes. I have a 1. Does this set contain a 1? Yes. How about a 3? I got a 3. How about a 3? I got a 3. How about a 5? I got a 5. How about a 5? I got a 5. The fact that there are more, I can't tell them apart, can I? I hate this. However, these are indistinguishable objects. If they are different somehow, like I would have the first one and the second one somehow be different, then I could make them different sets. But right now, you can't tell them apart. So yes, the one that's there is the one that's here. This one is that one, is this one. They're all the same one. But there are more of them. No. I don't like it. So we'll talk about distinguishable objects and indistinguishable objects. And that'll matter a little later. Questions? I earlier said I had one child, and that child was not a daughter. Therefore, when I talk about the set of my daughters, that's a set with no elements. This is called a null set, or an empty set, and is often given the symbol of a 0 with a slash through it. This is part of why the computer science notation that used to use 0 and then O, and the 0 would have a slash, it made me twitchy, because that symbol doesn't mean 0 to me, it means an empty set. It isn't quite the Greek lowercase letter phi. It isn't quite the uppercase Greek letter phi. It's a different kind of thing. But I'm handwriting and I don't have a perfect font, so we'll have to be careful. On the other hand, that is indistinguishable. However, a singleton set, that should be one word, has one element. However, based off of this idea, I could write that one as many times as I want, shouldn't I? Ugh, I hate this. By the way, this is not an empty set. What is that? No, it's just a set of an empty set, right? There's only one in there. In a real sense, this is like buying an empty box off of Amazon. Right? An empty set would be an empty box, wouldn't it? So here's your empty box. I gave you one empty box. I delivered to you one empty box. So if you mean an empty set, use this or this, don't use them both. That's not empty. I did say I wanted to draw pictures. Usually, I think of the set as being part of some universe of discourse. Like we were talking about the domain for our propositional variables, right? X is a person, X is an integer, X is a real number, X is an animal. All rabbits hum. I remember this game. Okay, so if I have in some universe of discourse, usually we'll write U for a universal set. Hey, this is the set of all the crap I'm talking about. Then I'll write a big box for my set U. And I will represent a given set in this universe as a shape. I do a circle. So here's an example. In the universe of English letters, let's write vowels. Letters that are always vowels. Right? A, E, I, O, U. Then all the other letters go out there. If my universe of discourse is colors, I could create the set P for primary colors. Now, primary colors red, blue, and green. Primary colors for light are red, blue, and green. If you mix these colors by shining colored lights down, well, you can combine them and get all the other colors that exist in the spectrum. By the way, we call them primary because they're the ones that we have receptors for in the back of our eyeballs, red and green and blue receptors. People who are colorblind or who have damaged color receptors might not always be able to see all of these things. Some animals have more color receptors. Some animals have fewer color receptors. Dogs, as far as I know, have 2 color receptors. Mantis shrimp have 12. They see 12 different colors of which we don't know any of them. Specifically, things that are triggered by specific wavelengths in the back of their eyes. Questions? There's a name for these types of pictures. Anybody know it? It's named after the person who came up with the idea. They're called Venn diagrams. Insert bad joke here. I don't always make diagrams, but then I do. Oops. My wife got me that on a t-shirt. I want to sometimes deal with more than one set, in which case I might have 2 or more circles inside my box. On our Canvas page, there is a link to a paper called the Venn Diagram Survey website, the Venn Diagram Survey. And it's very interesting about the way in which we draw Venn diagrams, because the way in which we draw them limits us on the types of things we can do. More on that later, but I think that's worth looking at. If I have 2 sets that live in the same universe, I can say that A is kind of a rounded off less than or equal to. A is a subset of B. Well, what's the definition of being a subset? Oh, if for all A in A is also in B. Every member of A is also in B. Actually, I don't really need the universal. If it's true that every A is in B and every B is in A, well, then those 2 sets will be equal, right? That's why the equal sign is there. If I want to say that there's more stuff in B than there is in A, I'll typically write it without. What's the Venn diagram picture look like for a subset?
Is it going to be 2 circles with like that overlap number?
For a subset, I want to have this behavior. So yeah, I want 2 circles, but I want the entirety of A contained inside B. Inside whatever universe I'm working in. By the way, the following statements, I hope, are 2 of the easiest proofs you will ever do. No matter what set S is, the empty set is a subset of it. And the whole set is a subset. Here's the fun part. I want to prove these. Each proof is one line long. In order for me to show that the empty set is a subset of S, I need to show this is true. So let's instantiate. Let's pick an element in the empty set.
There's nothing.
There isn't one. Which means this if-then statement starts with a false. And F arrow anything is automatically true. This is a vacuous proof. The second one is a trivially true statement. Because for the second one, I need to show if you pick an element of S, then it's in S. But if you pick an element of S, it's in S, isn't it? I'm done. You told me to pick something in S. That's the conclusion. Something arrow T is automatically true. Pick something in the bag. Is it in the bag? By Jove, I think she got it. Showing containment. Showing that one set is contained in another is the basis for showing two sets are equal. I want to show that every element of the first set is in the second set. So if I want to show that A and B are the same, I can say, hey, look, all the things that are in A are in B, and all the things that are in B are in A. So it's almost always easier to show the containment. And by the way, Gracie, this is why I was able to justify that other statement. Ready? Two sets, A, B. That 1 is in here. That 3 is in here. That 5 is in here. Now go the other way. This 1 is in here. This 1 is in here. Because they're indistinguishable from one another. Questions? It is possible to make a set out of other sets. Here is a set. The set contains 4 things. It contains an empty set. It contains a set with the letter A in it. It contains a set with the letter B in it. And it contains a set with both the letter A and the letter B in it. So this is a set with 4 distinct items in it. I did not pull this set out of thin air. consider just this first piece, the set AB. There are subsets of this set, yes? But from the thing we just proved, I know the empty set is one of those subsets. I know the whole set is one of those subsets, right? So this is a subset of this. This is a subset of this. Isn't this a subset as well? Isn't this a subset as well? This is actually a collection of subsets. It's all the possible subsets of this thing. If we have a set with a name, let's call this set S, then I will call this collection the power set of S. Oops. If I want to write it in a set builder definition, I can write it like that. I said something earlier. I said that that particular power set that I gave as an example had 4 distinct elements in it. That previously ugly set, 1, 1, 3, 3, 3, 5, 5, 5, 5, has 3 distinct things in it. So did the set 5, 3, 1. For any given set, we talk about the cardinality of the set S. We use absolute value bars, but this is really talking about size. The cardinality of S is the non-negative integer n so that S contains exactly n distinct elements. And now we get to that heart of the matter of being distinguishable versus indistinguishable. If I can tell the items apart, then I count them separately. If no such n exists, we say the set S is infinite. Otherwise, n is a finite value. I could have billions and billions of things. As long as it is a finite number, that's fine. Questions? So right now, the cardinality of the empty set is 0. The cardinality of the set 1, 1, 3, 3, 3, 5, 5, 5, 5 is 3. The set with the natural numbers is infinite. So is the set of real numbers. So is the set of complex numbers. But that's our symbol. In the textbook, it was a bold-faced letter, right? For N. I don't have bold-face pen. So we're going to write an extra wide line for the boldface part. Those are the integers, the natural numbers, the real numbers, and the complex numbers, respectively. I don't have boldface, otherwise I'd do it that. By the way, that particular font is known as Blackboard Bold. It was a way to make Blackboard writing bold when you only had one color of chalk. A question we should be able to answer, but I'm not going to answer here. I want you to think about it. If S is finite, what is the cardinality of the power set? I don't want to answer that one right now. Think about it. We'll talk more about that in a week and a half. More questions. Ask me more questions. My buddy Rene Descartes, when talking about sets, came up with this idea of a Cartesian product. And in a Cartesian product, the order in which I write things starts to matter. So instead of using set braces, the squiggly ones, I'm going to create an ordered list. You saw this in algebra class, you saw this in calculus class, you saw this in trig, and you didn't think anything of it. We called them ordered pairs, right? X, Y. They were in order. Well, what that's really saying is that when I have two sets, A and B sets, the product A times B is a new set made of things of the format A comma B, so that A is in A and B is in B. So when we talked about ordered pairs, we had a number comma another number, and we said the first number is a horizontal number and the second number is a vertical number, and they were really R and R, so I made the coordinate plane out of it, the Cartesian plane. But I don't have to have just two. I can have as many as I want. I can even have infinite products where I just keep going and each one comes from the right set. But the sets don't have to have anything particular to do with each other. Here's an example. The set A is the number 0, 1, and the set B is the letters ABC. If I want the Cartesian product, A cross B, I'm going to build ordered pairs. 0A, 1A, 0B, 1B, and 0C, 1C. And this set has 6 distinguishable elements. If you really wanted to, you could think of this exactly the same way as I was just talking about ordered pairs. I can have an A axis and a B axis. And if we go by ordered pairs, then this first dot right here is 0A. And this dot, 1B, that's this one up here. And 0C is here, and 1C is that. You could label all of these with these 6, couldn't you? All right. If I think about ordered pairs, when I have 3 of them, we call it an ordered triple. If I call it 4 of them, it's a quadruple. A 5 would be a quintuple. 6 would be a sextuple. The word tuple is meaning an ordered collection. So if I have n of them, it'll be an n-tuple. I hate that word. It's just so awkward sounding. A1, A2, up to AN, where AI is an element of capital AI for all I. In algebra, we deal with the real numbers by the real numbers, the Euclidean Cartesian plane. But I can do 3-dimensional space, right? R times R times R, X, Y, Z. If you really want to think about it, you could do X, Y, Z, T. Have a 4th dimension in that, right? You just have a list of ordered 4. You can have a list of order anything. Linear algebra deals with lists of orders as many as we want. 2 n-tuples are equal if all of the corresponding entries are equal. If they're different even once, they're different things. Frequently, if we want to use a quantifier for a property, I should indicate the set. We were talking earlier about a proposition P of X, right? And normally I would write for all X, P of X. But we had to know what set we were working with. Sometimes it's worth specifying that set right here. For all X in the set S, this little symbol means is in, or is an element of, or belongs to. You can read it all 3 ways. And so when we use quantifiers, we will frequently indicate the domain of discussion in our quantifier by explicitly stating the domain. Hey, we're working out of this set. If we don't, then somewhere else we have to have said what we're working as. Because if I talk about for all X, these numbers are even, then I better say no in advance. I'm talking about numbers. I can't say students are even. Are you even? I know I'm odd, but that's a separate problem. Okay. A subset of a Cartesian product is a relation. This is an interesting idea. that we will come back to later. If R is a subset of A cross B, then R is called a relation from A to B. We will come back to that idea. But I won't do it today because I just hit the clock. So I will see you all on Wednesday. Have a wonderful rest of your day.